Hi there, AP Calc students. This is Lesson 7.5, Applications from Science and Statistics. I believe this will be our last home lesson video, and so probably you're excited to hear about that. We're going to do a couple of examples here. We're going to really just focus in on a couple of types of problems here. There's Puma walking around here. Mainly the ones we're going to focus on are trying to figure out the amount of work done to pump some kind of water either up or down from some kind of a tank. And we've seen a little bit of this before when we did some related rate type things, but this will be actually the work done in trying to get rid of this water. Alright, so here we go. Here's the first example here. So this is a cylindrical reservoir of diameter 4 feet and height 6 feet, half full of water weighing 10 pounds per cubic foot. Find the work done in emptying the water over the top. Alright, first thing I'm going to do is try to draw this here a little bit. So here's my cylinder right here, and I'm going to try to label some of the things here a bit. So it does have some water in it. It's filled up half full, it says, right? And so I'm going to try to label some of these key things here. So I know this is 6 feet tall, from there to there, 6 feet. I know that the radius here of this water, if I try to draw that in here like that, I know that that radius here is going to be 2, I believe, diameter 4 feet, radius 2. And something else that we'll really try to consider here, and this will be quite important as we go later on. Don't, Puma, don't do that. Puma's trying to get into some banana bars there. It's kind of silly. So I'm going to call this 6 minus h. The total height there is 6. That distance from where that water is to the top, we're just going to call it 6 minus h. Right now we know that that's 3 feet tall, but don't, Puma, don't. Come on. Here we go. Okay. So anyway, a couple key things to keep in mind here. Work in these types of situations is going to be defined as density. So that has something to do with how much the liquid weighs times volume times distance, because in this case we're going to actually be moving some liquid a certain value here. I'm going to change my pen width a little bit so you can see a bit better. Alright, so once again we're going to try to think of the disk method in a sense, trying to think of a slice of what this volume would look like. And so I think you see that the volume of this slice that we're going to make here, well, that's going to be pi r squared times the height. And so in this case, we know that the radius for sure, since this is a cylinder, is going to be 2, and 2 squared is 4, so it's going to be 4 pi. Now the actual height here is something that we don't know exactly, although we're going to label it as this 6 minus h, like that. Okay? So then if I actually figure out my work that I do here, and I'm going to switch colors here. So the change in work is actually going to be 10, and 10 comes from that density that they give us here, and the volume then is going to be this 4 pi times that height, and then the height that we try to move this at is going to be that 6 minus h, like that. Now keep in mind that's only for this one slice that we have here, and so I want to integrate it so I can get the volume for the whole situation here. So my work that I'm going to end up doing here, 4 pi times 10 is going to be 40 pi. And I'm going to integrate this from 0 to 3. Now, where does 3 come from? Well, we know that 3 is that, whoops, I don't want to use my eraser there. Here's what I want. That 3 is my distance from here to here. The water is half full, so that's where that comes from. And then I'm going to do, so what's left then is this 6 minus h, and I'm going to call that dH. Anyway, I'm going to go on to the next page here and continue on so I have enough room to keep working here. So what I really end up with then is 40 pi. I can pull that out, and if I do my integral, which is just 6 minus y, the integral of that is going to be 6y minus y squared over 2. Your powers increase, remember. And I'm going to evaluate that from 3 to 0. So anyway, that's going to be 40 pi, and if I go ahead and put 3 in place of my y value there, my h is going to be 18 minus 3 squared is 9 minus 4.5, and when I put 0 in there, of course, I'm just going to get 0. So anyway, this is going to end up to be 40 pi times 13.5, and that's going to equal about 540 pi, and the units there are going to be foot-pounds. We'll talk more about that as we go. So again, that's a pretty basic example. We're going to be doing some variety of examples related to this and problems related to this, but let's move on to our next one, which will be just a little bit more challenging. This one is going to be now the volume of a cone. So we have this inverted cone, height of 15 meters. You can tell by this diagram, base of 4 meters, filled with water to a depth of 12 meters. You can see that right on here. Here's the depth of the water. Determine the amount of work needed to pump all the water to the top of the tank. Assume that the density of the water is 1,000 kilograms per meter. Now, we would probably agree here in a case like this that we could still do a little slice here just like we did with the cylinder, but as we can tell, that slice is going to change as we move up this particular cone. But we still know, if we're looking for a particular cylinder here, that that volume would be pi r squared times h. And again, we can kind of visualize that little cylinder right in here. We're going to keep taking several of those cylinders and adding them up in order to figure out how much work is done. Well, in this case then, when I get to my work here, I need that 1,000 in there because that's your density, so to speak. It is the density, and so I need to multiply that by pi r squared h. Now, here's the trouble with these kind of problems is that we have two different variables. We have an r and an h, and so most of the time on these kind of cone problems, and I think you might remember this from when we did this back a few chapters ago, we want to try to consolidate this into just one variable because we don't know how to integrate with two different variables like this. So most of the time what we do then is we try to look at the two similar triangles that we have here. So we have a small one and we have a big one, and we try to visualize what the radius and the height would be of each one. So of the very biggest one, we see that the radius up here would be 4, and then that height, which the problem tells us is that whole distance there, would be 15. Meanwhile, on the smaller one, then we'll just call the radius r, and then that height h, because that's going to be continually changing. So what we like to do then is set up a little proportion that r over h will equal 4 over 15. And if I solve this for r, then I think you can see that r will end up to be 4h over 15. So when I go back and substitute that into that particular volume thing that I just did then, I would put this, change this, I would put this 4H over 15 in place of this R right here. And so then what I'm going to have is 1,000 pi, but not R. I'm going to put 4H over 15, and I need to square that, and then I'm going to multiply that by the height. Anyway, if you multiply all this stuff out, here's what you're going to actually end up getting. You're going to get, let's see, I think I'm going to erase this thing right here. You are going to get 640 pi over 9. That accounts for all those numbers there. And I'm going to have an h squared. And here's the tricky part right here. This distance right up here, which is that distance I need to pump that water up. I need to pump it up that high. How high is that going to be? Well, it's less than 15 because that's the total distance. We're going to actually call that 15 minus h. We'll see that quite a bit in these types of problems. So that's what I'm going to put in place of my actual height there. I'm going to put 15 minus h. So again, that's a representation of the work that has to be done for that particular slice that we have right there. Proceed on to the next slide here and show you what we're going to do. So I'm going to integrate this from 0 to 12. Now you might wonder where that comes from. Hi there.
I'm going to get some water.
Oh, good. So you can, let's see, there's a spigot right over there, and if there's a glass right in that thing right there, yeah. This is good. You're going to get on my home lesson that I'm recording right now.
Ah, okay, I'm sorry.
No, that's okay.
You should totally leave that in there.
Oh, I'm going to, yeah. Because my cat interrupted me a little bit earlier, so.
Oh, yeah. Can I take this out?
Yeah, no problem.
Thank you.
Yep, see ya. All right, so proceeding onward here. Now, where does 9.8 come from? Now, sometimes the problems will use this and sometimes not. I'm including this in here because 9.8, of course, is that acceleration due to gravity. And so we have to account for that if we're pumping this water up out of that particular tank. Now, if I multiply that h squared by 15 minus h from the previous slide, I'm going to get 15 h squared minus h to the third. And again, there needs to be a dh in there, of course, as we have for all integrals. And so what I end up with here, and now Puma's trying to get at some chicken salad, just a second here. Alright, now I'm back. And I'm going to try to wrap this up because this is getting a little bit long. But again, remember all this stuff here is going to be a constant, so I can pull that out in front. Really, I just need to integrate this part right here. So I think you can see that this is going to be 5h to the third minus h to the fourth over 4. I want to evaluate that from 0 to 12. And then I'm going to have to multiply it by all this stuff right here. Should be multiplied in front of all that. So because I'm rapidly running out of time, I'm just going to tell you that this is approximately equal to 7,566,362 joules, which is that total amount of work that needs to be done in order to pump all of that water out of that inverted cone. Anyway, as I said, we'll be practicing on this a lot. We're just going to focus in on these types of problems for the ones that you get and are going to present to other people. So thanks for watching and being patient through this whole process this year, and we'll see you guys in class.